In the previous videos, we have been discussing how to find the area under a given curve. For example, a curve like this. This could be our f of x and the area under the curve between A and B. Okay, and we found that there were one possibility was to approximate using rectangles. Okay, in that case, we would be underestimating, like in this case, or we could be overestimating if we chose different rectangles. Okay, so in this case, we have the yellow ones are what we called right approximations. Okay, and we denoted Rn, the right approximation, with n rectangles. And then here, the red rectangles are what we called left approximations. With n rectangles. Okay, and we discussed that the limit as n tends to infinity of these right approximations and the limit of these left approximations both converge to the same thing and both converge to the area under the curve. Okay, of course between A and B. I have compared this before to the resolution in a picture in the computer. Okay, you see the pixels until you don't see them. Okay, that happens when the pixels become very small. So if these rectangles become very narrow, okay, we put more and more and more rectangles, there will be at some point we will not be able to see any difference between the actual area under the curve and the area approximated with the rectangles. Okay, so we define, actually we are going, instead of talking about area under F all the time, we are going to define the definite integral from A to B of f of x dx. This is precisely these limits of the left and right approximations. Okay, so this is how we define, this is the definition of the definite integral. This is called the definite integral of f from A to B. Okay, and here it's important to notice the integral from A to B of f of x dx is the signed area. Okay, and this is very important, between the graph of f and the x-axis. Of course, between x equal a and x equals b. Okay, so this is important to keep in mind, because whenever we have a function f that changes sign, okay, it will be very important to take into account that the sign matters. Okay, so here, if this is A and this is B, the yellow area would be a positive area. Okay, but then the blue area would appear subtracting, so minus the area below the x-axis. Okay, and it's always the area between the curve and the axis. So for instance, let's do an example. This is very important. The definition of the integral is the area. Okay, it's the limit of the approximations, but the limit of the approximations is the area itself. So we need to keep this notion in mind very clearly, that when we are computing the integral from a to b, from -4 to 2 in this case, what we are actually computing is a signed area. So let's do it for this function, 1/2 of x plus 1. Okay, so it's an area, so we can actually plot the graph. Okay, this is 1, -2. At x equals -2, the function crosses, there we go, crosses the x-axis. Okay, and then it crosses the y-axis at y equal 1. Okay, when x is 0, the y is 1. And we want to go from -4, which will be, let's move this over here, will be somewhere here. Okay, this would be -4. We want to go all the way to 2, which will be here. So the area that we are looking at is the area between the x-axis and the graph of the function. And again, we need to keep in mind that there is a negative portion wherever the function is negative, and then there is a positive portion. Okay. So we can now compute this line I did was 1/2 of x plus 1, just in case. This is my f of x in this case. And this is my a, and this is my b. A is -4, b is 2 in this case. Okay, so the integral from -4 to 2 of 1/2 x plus 1 dx is the signed area, and that is, well, the green area. Well, what happened there? Let's just go ahead and do the computation. So this is the green triangle has a base that is 4 units long. Okay, and it has a height that is equal to 2. Okay, because this height here, when I plug in x equal 2, I get 1 plus 1 makes 2. So 4 times 2, and then I have to take half of that because it's a triangle. Okay, so that goes with a plus. And then we can put the negative area here that has the triangle has a base that is 2 units long and a height that is 1 unit long, because at x equal -4, okay, I get -2 plus 1, -1. That means a negative height pointing down of 1 unit. Okay, so these two together, this cancel out, so it's 4 minus 1, that makes 3. Okay, so the area between the curve and the x-axis is equal to 3, and that is the value of the definite integral. Okay, notice here the definite integral is a number. It's an area. An area is given in with a number. We can do one more example. We can do the definite integral from -4 to 4 of 1 plus, this is going to be a more complicated one, 1 plus square root of 16 minus x squared dx. Okay, and because we know this is a signed area, we need to relate these two areas somehow. Okay, here notice the equation of a circle, this is something we need to know, okay? X minus x0 squared plus y minus y0 squared equal r squared. This is a circle with center x0, y0, and radius r, okay? It is very important that we remember this formula. We use it once in a while, so we need to memorize it. Now, why am I mentioning this? Because if I write the function here, f of x, that I have, I write 1 plus square root of 16 minus x squared. What do I get? So y minus 1 equals 16 minus x squared, the square root, right? But then I can take squares on both sides. And look at what we have. We have x squared plus y minus 1 squared equal 4 squared. Okay, so if we compare with the previous formula, with the template for the equation of a circle, this is a circle with center 0, 1 and radius 4. That is important, okay, because it will allow us to plot the shape we are finding the area of, okay? But also, I wanted to emphasize, looking at the here at this equation of the circle, this is an implicit equation. Y is defined as a function of x implicitly, but we can solve for y. Okay, and we are going to get two possibilities. The plus and minus square root of r squared minus x0 squared. And then we can move there we go. We can write it like this. Okay, and this is the two choices, plus or minus, give you the two half circles. So if this is x0, y0, and this is r, okay, so we have the plus square root, and we have the minus square root. That's something to keep in mind for the future. So this is the minus square root. So what do we do with this? Well, once we know that we can draw the circle, right? And according to the template, the center is 0, 1, and the radius is 4. Okay, so that means the x-axis is going to be somewhere here. Yeah, so 1 unit down, and then this is going to be the y-axis. Okay, notice here, so this is like 1 unit up, and then we have here, this is -4, and this is 4. Okay, because that is the radius. And then we want to get the area here under this piece here, okay? Because see how it is, you see here that it comes with a plus, so it's 1 plus something, so we are looking at See, compared with the template, we are looking at the plus square root, so that's the upper part of the circle. So the area we want is the whole area here. That doesn't look very good. Let's use, there we go. This area over here. Okay. Notice that it has two parts. It's half a circle, but then it's lifted up a little bit. So we need to account for that too. -4 to 4, 1 plus square root of 16 minus x4 dx. So this is the signed area. So we have the rectangle. And then we need to add the semicircle. Okay, I'm writing it. You see that I'm describing it just with a picture, but I think the idea is more clear this way. So we have a rectangle that is 8 units long and then 1 unit high. And then we have a semicircle that has a radius of 4 units. Let's instead do like this, 4. So this is very easy to compute. So it's 1 times 8 plus pi times r squared, and then I have to divide by 2 because it's half a circle. Okay, so that's it. So this is 8 plus 16 pi divided by 2, so 8 pi. So 8 pi plus 1. And that is the final value of the area.